Welcome back. So this is chapter 3, applications of differentiation. Okay. The very first section 3.1 is about maximum and minimum values. We had started this section in the class, so let me go over it quickly. Some of the most important applications of differential calculus are optimization problems. Optimization problems means problems in which we are required to find the optimal or the best way of doing something. These can be done by finding the maximum or minimum values of a function. So a problem could ask you to find the maximum value or a minimum value. Such problems are called optimization problems. All right. Next, let's understand maximum and minimum values. Let us first explain exactly what we mean by maximum and minimum values. We see that the highest point on the graph of a function f, here is graph of a function f, is a point 3,5. This is the highest point. So that is 3x coordinate. And notice point 3 gets y coordinate 5. So that point is 3, 5. It is the highest point of the graph. Okay. So the largest, so what does that reflect? It means the largest value of f is 5. So when you say 0.35, 5 is the value. So the highest value, the largest value is 5. And where exactly do you get that highest value? At 3. It's at 3 that you have the largest value. Likewise, in this graph, the value means height. The smallest height is 2. And where do you get that value 2? At 6. So f at 6 is 2, 2 being the smallest value. Next, we say that f3 equals 5 is the absolute maximum of f. f6 equals 2 is the absolute minimum. All right, so let me remind you, absolute, the highest in the entire graph is at 5, the value is 5. The lowest value of the graph is 2. Okay, so that is why they are called absolute. So what is the definition of absolute? Let C be a number in the domain D of your function. Then f of C is the absolute maximum value of f on D if f at C is greater equals f of x for all x in D. Maximum means you have to be bigger or equal. So f of C is bigger or equal f of x for all x. Absolute minimum value means what? Your value at C is less than. That's what makes it minimum. So you could have absolute maximum. To be absolute maximum, you have to be greater or equal all other fx's in your D, D being the domain. Domain is where your function is defined. For example, in the previous case, domain starts from 1 until 7. You see? So domain of this function is 1 until 7. Absolute maximum value is 5, achieved at 3. Absolute minimum value is 2, achieved at 6. Okay? So again, definition, you say f of C is the absolute maximum value of f on your domain D if f of C is greater or equals f of x for all x in D. Likewise, your value f of C is called the absolute minimum value of f on D if f of C is less than or equal to f of x for all x in D. An absolute maximum or minimum is sometimes called global maximum or minimum. So some authors call absolute to be global. That's fine. Okay. The maximum and minimum values of f are called extreme values. Okay, extreme means you could be maximum or minimum. Extreme. Okay, figure 2. So here is figure 2. Shows a graph of a function f with absolute maximum at d, absolute minimum at a. So let me worry about maximum. Maximum is the highest. So where do I get the highest? At d. Now if I look at the minimum, this looks like the minimum height, right? Not this. This is the minimum. Where do I get it? At a. Note that DFD is the highest point on the graph and AFA is the lowest point. In figure 2, we consider only values of x near B. For instance, so where is our B? Here we go. All right. If we restrict our attention to the interval A to C, A to C, then FB is the largest value. So in other words, look, if you go from here to here, B gets the maximum height because I'm not worried about the rest of the graph. From A to C, B gets the maximum height. All right. So such a point, BFB, yeah, is called local maximum. Local means in a small region, it is maximum. Okay. I'll stop this video for now so that I don't go beyond a certain time. Okay. Continuing soon.